Well, thank you, and thank you for the invitation. Um, Thankfully, Min-Kun has done a lot of the background for me already, so I can skip through or go a bit quicker through a lot of this stuff because I'm going to be working this Weil-Petersson model again, like Min-Kun mentioned. So he's also mentioned some of the background results on spectral gaps of Laplacians and hyperbolic surfaces, so that job's done for me too, but okay, I'll give a bit more details. And what I want to talk about is some recent work with Will Hyde and Davide Macera, where we find a new proof of this 1/4 spectral gap result using this so-called polynomial method from Chen, Garza-Vargas, Tropp, and Handel from 2024, which was used to prove some results on something called strong convergence of random matrix ensembles and group representations. Okay, so I'll talk about all of these ideas and compare it to the previous methods of these results Min-Kun highlighted previously. So let me just set the scene. So the scene's identical to what Min-Kun looked at. So it's just going to be closed, so compact, no boundary, connected orientable hyperbolic surfaces. Topologically, it's specified by some topological parameter, the genus G. For me, it's going to be at least 2, so we have a nice hyperbolic metric on these things. So as Min-Kun said, these are things locally isometric to, well, your favorite model of hyperbolic space. For me, it's the upper half plane, so it's just your upper complex plane, has some nice metric on it so that distances get stretched as you go towards the real axis. So here's an atypical looking hyperbolic surface because my genus aren't arranged nice enough, as Min-Kun pointed out. But yeah, here's a mental picture to have in mind if you want. So, and the thing I'm interested in is the Laplacian acting on L2 functions. So if you want to work on the universal cover, the hyperbolic space, it's just your usual Euclidean Laplacian in the coordinates with some scaling by the imaginary part. And I have this minus sign here to make it a nice positive operator. So it's going to be self-adjoint, it's going to be a positive operator. So if I look at the spectrum of this thing, it's going to be just discrete. So it's just going to consist of eigenvalues, and they're going to be non-negative eigenvalues. So the first eigenvalue that you always get is this 0 eigenvalue. And this is just coming from constant functions. I'm on L2 functions, my space is compact, it's finite volume. So my constant functions are L2, I hit them with the Laplacian, I just get 0. It's a simple eigenvalue because I'm assuming my surface to be connected. If it was disconnected, I'd get a multiplicity for every connected component, okay? So the next thing that we're interested in is this lambda 1. So it's the first non-negative eigenvalue in this setting because I'm connected. And it's important for a multitude of reasons. Min-Kun highlighted a lot how it's related to, say, the geometry of the surface, so through connectivity issues like the Cheeger constant. It's also related to the geodesic flow. So on these, the geodesic flow is exponentially mixing. Lambda 1 governs the rate at which this exponential mixing happens. So it tells you a lot about the surface. And what I'm interested in is what this lambda 1 looks like on a typical surface in some random model. It'll be the Weil-Petersson model, but there's several models you can think of. But let's just be vague at the moment, think of some typical surface, okay? So if I work deterministically, there's this classical result of Huber and there's quantitative versions of this, say due to Cheng, that tells me if I look at a sequence of surfaces with genera going off to infinity or a diverging diameter, I look at lambda 1 along this sequence, I look at the limb sup, it's bounded above by 1/4. So where does this 1/4 come from? It's if I look at the hyperbolic plane, I can look at the Laplacian on the hyperbolic plane. Its spectrum is absolutely continuous, equals 1/4 to infinity. So this is the bottom of the spectrum of the universal cover of the hyperbolic plane. This is where this is coming from. And what we tend to see is that surfaces typically start to look like the universal cover as the genera goes to infinity. So what it's telling me is that if I want to look at a sequence of surfaces of large genus, or equivalently, this is large volume, I mean constant negative curvature, so Gauss-Bonnet tells me that these are linearly related, then 1/4 is just an asymptotically optimal spectral gap for these surfaces. And it took us a very long time, so until 2021, so a result of Hyde and McGee to actually prove that there exists a sequence of surfaces where this lambda 1 does actually go to 1/4. And it's, okay, so we still don't know actually an explicit construction of surfaces with this property. This is a probabilistic construction. So it's a big open question, well, what is an actual explicit sequence with this property?
So is this some analog of the Ramanujan graph in the discrete setting?
Yeah, it's exactly that. So 1/4 is the Ramanujan band for hyperbolic surfaces. Yeah.
But like there are explicit constructions on the graph side using some algebraic properties, but...
Yeah, there's explicit constructions there, but for surfaces, we have no idea, yeah. Okay, so I said deterministically 1/4 is the best we can hope for. And so why would we expect maybe typical surfaces should get to 1/4? Okay, so if I look at many random constructions of surfaces, so Weil-Petersson, or I can look at, say, fix a surface, look at random covers of this thing of a finite degree, or a fixed degree. There's finitely many of them. You can sample them uniformly, so this is another model of random surfaces. In many of these models, if I look at sequences of surfaces of growing genus, they have this property that they Benjamin-Schramm converge to the hyperbolic plane. So what I mean by this is if I look at the proportion of points, I fix some radius, I look at the proportion of points whose injectivity radius is smaller than this thing, and along this sequence, this proportion will go to 0. Okay, so in most places, you're looking like large balls isometric to the hyperbolic plane in this large genus limit. And what this often implies with some minor conditions, maybe you want some lower bound on the systole of these surfaces, that you have a weak convergence of the spectral measures. Okay, so the spectral measure for the Laplacian on my surface is I put a Dirac mass at every eigenvalue, normalized by the volume. I look at this sequence of probability measures, or look at this sequence of measures, sorry. It'll weak converge to the same thing, but on looking at the hyperbolic plane. And for the hyperbolic plane, this has a very explicit description. So it'll look something like this. So as I said, it's absolutely continuous, supported 1/4 to infinity. And here's its density. Okay. So it has this hyperbolic tangent function. So it will start to level off to something constant in the limit. But near 1/4, near this edge, it looks like a square root function. If you expand near this edge, it looks like a square root function. Okay, so this is the limiting spectral measure that we see. But we can't deduce much about it because you need something very quantitative to be able to really deduce what's happening around 1/4. So now let me say some physics which I know very little about, but the overarching thing that tells you a lot about what we should expect comes from this Mohica-Schianoni-Schmidt conjecture. And I'm lying a little bit about what it's saying here, but roughly what it's saying is that if I look at spaces where the geodesic flow is very chaotic, an example being these hyperbolic surfaces, I look at the spectral statistics of the Laplacian, or some Schrödinger operator. So this is looking at the quantum mechanical side of your picture. Then typically, if you look at things of large energy, so large eigenvalue, you should start to see that the spectral statistics resemble that of Gaussian orthogonal ensemble. Okay, so this nice random matrix ensemble. So this typically, this is stated for large energy, so large eigenvalue. But let's just suspend that for a second and think what happens across the whole spectrum, so near the edge as well. Well, if I look at this GOE, we know what the distribution of this thing is in the large parameter limit, the large dimension limit. It tends to this semicircle law. So it looks something like this, and depending on how you do your scaling and normalizations, let's say it's between -2 and 2. And around these edges, it looks like a square root function. Okay. And if I look at the eigenvalues that cluster around these edges, they start to become distributed, well, they become distributed according to this Tracy-Widom distribution. So a very broad goal, broad conjecture, is that maybe we start to see the same thing for our hyperbolic surfaces, the eigenvalues of the Laplacian for these hyperbolic surfaces. And the scaling that we will have to see, well, because our Plancherel measure, remember it was this hyperbolic tangent function, around the spectral edge, this 1/4, it had this square root behavior. It's very analogous to this semicircle law, it's the square root behavior around the edge. The scaling that we will have to do to see this Tracy-Widom distribution, we would expect to be like the volume to the 2/3, or the genus to the 2/3. So the bold conjecture is that if I center my eigenvalues, or λ1, around this 1/4 on the edge, do some appropriate scaling, then maybe we should expect to see Tracy-Widom in the limit. So this is the very broad goal, and we're nowhere near saying anything about this because, as Min-Kun mentioned, only last year we can actually even say that we get close to 1/4. Okay. So, but this is the big ideas in the back of your head that maybe you want to care about. So let me make things more concrete and tell you the model that I want to focus on. So this is this Weil-Petersson model. I don't need to say too much because we're all experts now, thanks to Min-Kun, but let me just give a very broad recap. So this is a model that took place on this moduli space. So it's your collection of these surfaces. The genus G is a fixed topology, identify up to isometry. Identifying up to isometries is fine because it means they have the same Laplacian spectrum. Okay, so the Laplacian's, the spectrum is still something well defined here. And then you can look at the universal cover. This is this Teichmuller space. You have this symplectic form, this Weil-Petersson form that Minkun mentioned. It's invariant under this mapping class group orbit. You can descend it to modulo space. You get something nice. But geometrically, we have this nice description that Minkun told us about coming from building these surfaces from pairs of pants. And as he said, if I fix boundary lengths, the geodesic boundary lengths as a unique one of these guys up to isometry, and then I can just start gluing them together to build a hyperbolic surface. So to be able to glue them, the boundaries have to have the same length. I glue them with isometries to ensure that I have a nice hyperbolic metric on the limiting thing, or on the constructed thing. Okay, so I'll end up with a surface after doing all these things. Okay, and then you have a nice coordinate system for this Teichmuller space, this universal cover, from just assigning different lengths and the choice of isometries at each boundary. Okay. Exactly as Minkun described, so you have 3g minus 3 length parameters for each pair of boundaries and 3g minus 3 choices of the twists coming from a choice of isometry of how you glue the boundaries together corresponding to a twisting. Okay, why do you have 3g minus 3? Well, it's just an Euler characteristic computation. The Euler characteristic of the pair of pants is -1. Of your whole surface, it's 2 minus 2g, so you need 2g minus 2 of these pants, 3 boundaries each, so there's 6g minus 6 boundaries, but they're paired off, so it's 3g minus 3 parameters. Okay. And then you have this nice magic formula of Weil-Petersson that tells you that this Weil-Petersson form the symplectic form is just a wedge product, the length and the twist parameters. Okay. And then I can wedge this up to get a volume form. It's a Lebesgue measure. After doing some nice normalizations, I descend it to my modulo space, I get this volume form. So roughly speaking, what I'm interested in is, because we know that this modulo space has finite volume, we normalize to get probability measure, and then we can ask the question, what's the behavior of lambda 1 for a typical surface sampled with respect to this thing as the genus goes to infinity? Because this is the regime in which we expect to see these spectral results happening. And there was nothing special about doing this for closed surfaces. You could have also done this for surfaces that have geodesic boundaries or cusps, and you get a very similar objects. Okay. And again, they're all finite volumes. And to understand this modulo space of a fixed genus, or a genus going to infinity without boundaries, you have to actually understand these other volumes where there are geodesic boundaries and they have some lengths. So it is important to also understand these things too. Okay. And so what I'm broadly interested in are results of this form. So for what values of delta, that lambda 1 is bigger than probability goes to 1 in this large genus limit. Okay. And as Minkun already told you the history, let me just go through it quickly. So the first result is due to Mizukani. So she gets this 0.024 roughly. I even have an extra degree, number here. So it's a bit more accurate. And this came through really studying this Cheeger constant. So the Cheeger constant is related to lambda 1. You have lambda 1 bounded below by 1/4 times the Cheeger constant of your surface squared. So this is why it has this funny form 1/4 times something squared. And this is she found a lower bound for this Cheeger constant to get this. And then you have these quite some time before you see some more results, and you have these two independent teams, Wu and Shui and Lipnowski and Wright. In fact, these papers came out about 2 weeks apart from each other, so you have a big gap and then just 2 papers side by side, where they both improved this to, say, 3/16 minus some arbitrarily small epsilon. And then you had an Anthem and Monk that get it to 2/9, and 2 years later, and then finally last year to 1/4. But remember, the goal, the ultimate goal, at least for me, is to, well, see, can you relate it to some random matrix statistics? So this Tracy-Widden distribution. So this is nice, it gets you to the optimal thing, but we also want to understand this epsilon here, because this epsilon should be, optimally, what should we see is that if those Tracy-Widden conjecture that I said before was correct, that we should be able to get 1 over g to the 2/3 here, or something like this. This is the optimal thing that we want to actually see to relate it to these random matrix conjectures. Okay, and these last 3 bullet points, these 4 papers, are all based on what's called the trace method in this area. So it uses the Selberg trace formula. But what the trace method means is that you have to understand the geometry of closed geodesics on these surfaces of very, very long length. And these can be extremely complicated. And so to get these better and better bounds, you have to get more and more information about these things. And this final work is several papers, and it's like over 300 pages long, the level of detail that you have to understand these things. And it's very, very complicated. So last year, Will, Davide, and myself, we found another proof of this result that uses much, much softer geometric inputs. So you don't have to actually understand these geodesics of a long length anymore. And it's based on this, as I said, this polynomial method that was used to prove these strong convergence results in 2024 due to Chen, Garza-Vargas, Tropp, and Van Handel. But not only do we get a new proof, we actually get an explicit rate, and it's this polynomial rate. Okay, so we jump straight to a nice polynomial rate. And in theory, if you're really careful with our work, you could get something explicit for this C, but it's not worth the time getting. It's probably very, very bad. So for the extra 20 pages probably to compute this thing, we decided not to bother. Okay, it uses this polynomial method along with this trace formula that Min-Kun alluded to in his talk also. And along the way, the main technical tool that we have to develop is understanding these Weil-Petersson volumes of modulo spaces. Okay, so we need to develop brand new asymptotic expansions of these things, which haven't been done before in the level of detail that we needed to make them work with this polynomial method. But this is very technical in the bulk of our paper, and it's the ugly part. So I won't talk much about this. I'll talk about the general heuristics of these things. Okay, so if you've not seen the trace formula before, it may look a bit intimidating, but okay, this is what it is. What it is, it's just a formula that relates the spectrum of the Laplacian to the length of closed geodesics on your surface. Okay, it's nothing more than this. So if I look at the Laplacian on its own, it's an unbounded operator. I can't really take its trace. It's just going to be infinite. So I need to take some function of the Laplacian instead. Okay, so what we do is we just take some nice, smooth, compact supported function on the real line that's even for some technical conditions. I look at its Fourier transform. Okay, it's going to be a nice decaying function. I look at square root of the Laplacian minus 1/4, take the Fourier transform of f, evaluate it at this thing, and then compute the trace. It's a trace class operator now, so it's just the sum over the eigenvalues. Okay, so nothing too nasty going on the left-hand side there. Then on the right-hand side, we have these two terms. The first term is just something purely topological. Okay, as soon as I fix the genus of my surface, this thing only depends upon my test function, not the surface itself. And what you'll see appearing here is precisely this Plancherel measure of the hyperbolic plane of this limiting object that I mentioned before. And then you have the horrible part that you have to deal with, which is the sum over all of these closed geodesics. So this outer sum is these primitive-oriented closed geodesics. So these are, you have your closed geodesics, you can go around multiple times. We just go around them once. And the second summation does the going around multiple times. It's how many times you go around the same primitive curve. And then you have some ugly-looking function in terms of the length of these closed geodesics. But the important point is that it's just a function purely in terms of the length. Okay. So how do you use such a formula to get a spectral gap result? So as you can see on this left-hand side, we have all of the eigenvalues, not just lambda 1. So well, let's first fix some function. So let's just pick a nice function, like something like this. So it's going to be something that's non-negative, so we don't have to worry about what's going on here as much. Like with cancellations between terms, it's going to be something non-negative. It'll be even, and let's say it's compactly supported on minus 1 to 1. And it'll have some Fourier transform that looks something like this, okay? So an example of how to get something like this is just take a bump function on minus 1/2 to 1/2 and convolve it with itself, and you'll get something that looks like this. The key point is that on these small eigenvalues, so from 0 to 1/4, the input to this thing is something purely imaginary, right? And so just by properties of the Fourier transform, if I pick this thing nice enough, well, it's going to be something strictly decreasing here. And this is important because we want to be able to distinguish its value between different eigenvalues. After the 1/4, because when you're inputting imaginary values, this thing is going to have like some exponential size in terms of the support. You don't really see it here because it's just a fixed support. But on imaginary values, it'll have some exponential size in the support. And afterwards, it's going to be something oscillatory, but it'll be non-negative from the way I've chosen things here. But the important point is that its value doesn't exceed any, what you get at 1/4, so the edge of this spectrum. So it's all contained below here. It can oscillate a bit around, but it's going to go to 0 eventually. Okay. So just picture a function like this. And then, so what did these previous papers use? They use this classical moment method, essentially, for this set to understand this lambda1. And the idea is the following. So if I look at, say, the tth power of f hat, so of the left-hand side, so don't just look at f hat, look at f hat to the power t. On the geometric side, what does this do? Well, on the geometric side, I need to take the inverse Fourier transform, so it turns to a convolution. So I'll get, if I put this thing to the power t, I get the convolution of f with itself t times. Right? And what does this do? It stretches the support. So if it was supported -1 before, it's now supported minus t to t. So now I have to understand geodesics whose lengths are between minus t and t. Okay. Fine so far. On the spectral side, what does taking the tth power do? Well, as I said, the side, because the small eigenvalues, the eigenvalues below 1/4, they're a purely imaginary input into this f hat here. And this has size that's exponential in the size of the support. Okay. So what you see is you get some contribution to the spectral side that's of the order exponential times the constant times the size of the support, such that this constant will go to 0 as my lambda goes to 1/4. You'll turn to something oscillatory. And it will go to 1/2 as lambda goes to 0. This is just explicit computation. You can see this. So what the idea is well, what you'll see is because what this is saying is that eigenvalues close to 0 are going to give the most contribution to this spectral side. I always have this 0 eigenvalue. It's a trivial eigenvalue. It's always there coming from my constant functions. So I have to deal with it somehow. So the idea is first cancel this 0 eigenvalue. And the way you can do this probabilistically is see that it corresponds to something on the geometric side. And in this Weil-Petersson model, it corresponds to something very specific. It corresponds to primitive closed geodesics on the surface that when you cut along them, it doesn't separate your surface. Okay, so we know exactly what this corresponds to, and we've known this since the works of, say, these papers on 3/16. They've got 3/16. So we know already what this corresponds to here. And so if I do this cancellation probabilistically, so let's think I'm taking expectations, the leading order contribution now for the spectral side will come from like this lambda1, the thing that we care about. So the idea is to aim for a contradiction. You start to take this t larger and larger and larger. I've cancelled the 0 eigenvalue, so this is amplifying the contribution of lambda1. Right? And so if lambda1 is too small, the exponential contribution is going to be, we want to see that it's just too big. Right? But if I look at this trace formula, how large do I have to take this t to even hope to get a contradiction here? Well, if I'm taking lambda, so lambda1 is something smaller than 1/4, so it's like exponential to the constant t, so exponential, a constant that depends on lambda1 times t on the left-hand side. But on the right-hand side, this thing is supported on the bulk, so it's just something oscillatory. It's nothing too bad. It was polynomial independency in the t. But we have this g-1 factor here. So if we ever want to get a contradiction between this left-hand side and this right-hand side, this thing has to beat this g contribution, right? So what this is telling me is that t has to be on these scales some constant times log of g to have hope of getting this contradiction. But remember, t was the size of the support of this f. So what this is telling you is that to go for a contradiction, you need to understand closed geodesics whose length scale are like a constant times log of g. Right? And this is very, very horrible to understand at these length scales. And this is why these previous works really have to understand the geometry very, very well, up on very long length scales. Okay. So we don't want to go about this method. Okay? We want to do something different. And the idea of this polynomial method is to, rather than look at moments, let's just pretend for a moment that we, instead of taking moments of this f hat, we take some nice function h of this f hat instead. So this picture looks a bit messy, but let me break it down. What it's doing is, I fix my f hat that's supported in -1 to 1, so that was this nice function here. It's strictly decreasing on the small eigenvalues, so I can distinguish between two different eigenvalues. So what I want to do is I just want to take a bump function on where the eigenvalues from 0 to 1/4 minus epsilon get mapped to. Okay, so it's just going to be something that's 1 on the image of those eigenvalues under this map. Then what I want to do is I want it to go to 0 before I reach where 1/4 gets mapped to. I want to be looking at something that's going to be supported only on small eigenvalues for reasons you'll see later. So I need it to smooth out very, very rapidly on a scale epsilon down here. On the other end, I don't really care what it does because I don't have eigenvalues past 0 anyway. So let me just smooth it out on, I don't know, on a constant length scale. What this does is that because I'm smoothing out on a scale epsilon, you're going to see this epsilon coming into the derivatives of this bump function. Okay? This is an important point. So I want to look at h of this f hat of square root of the lambda minus 1/4. And why do I want to look at that? Well, it's just a simple thing from Markov's inequality. If I want to understand this probability that lambda 1 is smaller than this thing, okay, well, this is the same as if I look at the trace of this smooth bump function composed with f hat of square root of the Laplacian minus 1/4. That's the sum of the eigenvalues of h of f hat of this thing. Well, what value is this going to take? Well, for the 0 eigenvalue, I'm going to get a 1 here. That's always going to come into this trace. But if lambda 1 is smaller than this thing, I'm also going to get another 1 here. So this thing will be at least 2, right? So I'll take out the trivial eigenvalue contribution. That's where I over 2 gets mapped to, just because when I put 0 over here, I get I over 2. So this is the trivial eigenvalue contribution subtracted from this trace. And if I have this lambda 1 smaller than this thing, then this thing is at least 1. Okay? And then I just mark off inequality to say this is bounded by the expected trace of this thing. Okay? And so my goal is to see that this expectation just goes to 0 so that this probability goes to 0. So nothing too tricky going on there. The tricky part is, well, this is a smooth function. I want to put this into the trace formula. Well, for that, I need to take the inverse Fourier transform of this thing. Well, how the hell do you do that? Okay, so this is the hard part, right? But this is the nice thing about the polynomial method that gives us a way to do this, okay? So the desire for me is to understand this thing, right? This expected trace minus the trivial component. And what the polynomial method will allow me to do is obtain an expansion of this. I've only written it up to second order because that's all I need. But you can go to more orders. And in the expansion, what I'm going to see are some compactly supported distributions on the space of all smooth functions as the coefficients in this expansion. I've normalized by 1 over g here because remember that Plancherel term had a g factor in. So I just want the first term to be of constant order. That's why you're seeing a 1 over g factor coming out here. And there's a technical point that you're seeing that I'm not putting in exactly a smooth function here, and the reason is I want a trace class function, right? So I want these distributions to be on the space of smooth functions so I can use nice distribution theory to understand them. Well, I can't put any smooth function here. Imagine if I just put the constant function here, this thing's infinite. It's not even trace class, right? So I can't do that. So what I'm going to do is look at a smooth function that vanishes around 0. Because this f hat was Schwarz function, in a neighborhood, you're only going to see finitely many eigenvalues. So now it's going to be something that's nice and trace class. I can actually do the trace formula or expect to see an expansion. The error term is going to be some constant that depends upon the smooth function. And it's important to understand what this error term is to have something of sense from all of this. Okay. So since so we can use, if I have such an expansion for smooth functions, it works for the bump function that I mentioned for the reason that this f hat of 0, so where 1/4 gets mapped to, is something strictly positive. So our function h does vanish away from 0. So I can put h tilde as my nice bump function, h over x, plug it in here, and this thing will work. Now, the idea is to show that, okay, this new 0 and this new 1 are compactly supported distributions. In other words, there's some subset, some interval, closed interval in the real line, such that if I plug in a function supported away from that thing, these things will vanish. Okay? So, and for us, we will work out what it is because our new 0 and new 1 will be very explicit. We'll have very explicit formulae for them. And we'll be able to see that they're supported on minus f hat of 0 to f hat of 0. Now, what were these? This was where 1/4 gets mapped to. And remember the bulk spectrum, so all of the eigenvalues above 1/4 were contained from 0 to f hat of 0. So they're supported only on the bulk spectrum. So this is why we wanted this h to vanish away from the bulk spectrum, only on the small eigenvalues. Okay. So we'll have to obtain a result like this. And as I say, the control of this error term is very crucial because, well, if you have bad control over this thing, this is going to blow up because remember the h that we put in is this bump function that decays on this scale of epsilon. That's the scale that we wanted to smooth it out on. So if we have a bad dependency on here, this is going to be a bit meaningless for us. But what this polynomial method allows us to do is obtain a constant that's only going to depend on the suit norm of our function and its derivatives. So the suit norm of some number of derivatives of these things. And for our function that smooths out on this scale epsilon, in those derivatives, you'll see epsilon coming out. So you see the dependency to some power of the derivatives, and this is why you can take it to be a polynomial. Right? You can take it to be this thing nice and small, so this epsilon to the power minus m over 2 isn't going to kill the 1 over g decay that you got in the error term. So just as a summary, the polynomial method, rather than looking, so how do we get the expansion for smooth functions? The polynomial method, rather than looking at moments that are going off to infinity, we look at fixed moments. So first you look at a fixed moment and obtain some expansion in powers of 1 over g for this thing. Okay. And the error term in t can actually be quite bad. It's going to actually be like t to the power t. So it's going to be very, very ugly. But we're never going to really be taking t to infinity, so it's not going to matter. Once we have it for fixed moments, you can extend to polynomials, just linear combinations, triangle inequality. And then through a limiting procedure to get to a smooth function. So although the error term can be quite bad here, we've got to be able to control it somehow because we want to do a limiting procedure to get smooth functions, right? We need to get to this bump function h. So to get to these extensions, we have to use these classical inequalities for polynomials, and what they're going to do is, when I have a dependency that's like t to the t here, it's going to be like t to the t times the suit norm of my polynomial. But what these classical inequalities for polynomials will do, will be able to pull this t to the t into the norm and convert it into something that depends now on the derivative norm instead, suit norm of derivatives. This is the magic of these polynomial inequalities. And in doing so, okay, you'll do your expansion, you'll get some linear functionals on the space of polynomials, and you want to extend them to these compactly supported distributions. And then we'll use the random models, so this Weil-Petersson model and the geometry of our surfaces to compute their support. So when we, like I said, when we obtain the expansion for just polynomials, so you do fixed moments, you get polynomials just linearly, you're going to get some linear functionals as the constants in your expansion. And to extend them to things that are compactly supported distributions, you can use some nice inequalities. So you automatically can extend a linear function on the space of polynomials to one on a compactly supported distribution on smooth functions if you can prove a bound like the following. So it's a bound of like a constant times the degree of the polynomial to a power m times the suit norm of that polynomial on some interval. And the c, m, and k are going to be fixed. They are independent of the degree. And if you can prove such a bound, and this is going to be a very natural bound that comes out of this polynomial method, then you automatically get an extended linear functions to compactly supported distributions on the minus k to k. But you can say something a bit more. So once you know they extend, you can actually compute the support more precisely by just computing on moments. So all the time, we're always passing back to just fixed moments. So if you just look at if I plug in the function x to the power p into my functional, take 1 over p power, take the lim sup, and I find that this is uniformly bounded, then actually the support of my distributions are contained in this interval minus rho to rho. And this is what we'll be able to do, because for us, these functionals are going to be something very explicit, at least on polynomials. So how do we even get an expansion for fixed moments? Okay. Well, the idea is to go back to the trace formula. Remember, for the trace formula, when I put in a fixed moment on the geometric side, I had convolution theorem that tells me it's just powers of the fixed test function I put in. And for this, I can do some integration to be able to actually understand this. I want to understand the expectation of this thing. It's some function that just involves the lengths of closed geodesics, but as Ming-Kun pointed out, this beautiful toolkit of Mirzakhani tells us how to do integration of functions that involve lengths of closed geodesics. I'm lying slightly, she only told us how to do simple curves, but you can do non-simple curves too. And so what it does is this integration formula passes an expectation like this into an integral over real space that involves these Weil-Petersson volumes of modulo spaces of surfaces, but now with boundary. And the surfaces that you get is, I have some function in terms of some lengths of closed geodesics. I cut my surface along those closed geodesics. I'm going to get some disconnected surfaces, possibly with boundary. And it's these Weil-Petersson volumes of the moduli spaces of these surfaces that I'll see coming out. So to understand an expansion for powers, we're going to have to understand an expansion for these Weil-Petersson volumes. And this is the technical part of our work, is obtaining these expansions. And in particular, we show they have these sorts of Jevry statistics. So all in all, when you do this, we're going to obtain an expansion for this thing. So the trace of f hat to the power t, we'll be able to expand it up to, say, some order k for at least g big enough. And the error term that you're going to see is this horrible error term that I mentioned before. For its dependency on t, it's going to be like t to the power of like a constant times t, involving also how far into the expansion I want to go. So if you wanted to take t large here, this is just too bad. You can't do it if you depend it on g. But we have explicit formulae for at least the first two terms of this expansion. So the first term is probably what you expect. It's the leading order coming from the trace formula. It's coming from this Plancherel measure, and it's exactly what I get from the trace formula. The second term is coming from this Mirzakhani integration formula. It's expanding that expectation over lengths of closed geodesics, or this function over lengths of closed geodesics. And it's precisely the thing that you get when you restrict the closed geodesics to the ones that are simple, non-separating. So when I cut along them, my surface stays connected. Okay. And you'll get all of the k equals 1 to infinity. What you can notice is that this function here looks quite horrible for the term k equals 1, right? Because you're going to get a hyperbolic sign here. But for k equals 2 and beyond, it's bounded, but something uniform. So what you'll see is that when I want to eventually compute moments of this thing to actually understand these distributions, the k equals 1 term is going to cause a problem, because this isn't going to be something that's uniformly bounded for when I take t large. But we're saved, because remember, I don't want to look at just this expected trace. I want to look at this expected trace minus the trivial contribution. And it turns out that the trivial contribution corresponds very closely to the k equals 1 term. And this is what I said before, because the trivial contribution was the thing that we're always saying we have to extract, and it's precisely corresponding to the curves that are primitive, simple, and non-separated. Okay? This is what I mentioned before when I say we can cancel it probabilistically, even with these previous trace methods. It's seeing it exactly here as this k equals 1 term, roughly. Okay. And then, to get your expansion of polynomials, it's just linear combinations of these things. But there's a few nuances to this. Remember, all I wanted actually was a second order expansion of this expected trace. That was sufficient to get my spectral gap result. But I actually need to go higher order to make these things work. And the point is that, well, if I just do naive linear combinations of these things, what I'm going to get in the error term is, let's say my polynomial is, say, at to the power xt, something like this. In the error term, you'll see something that looks like this, say up to some degree q. But classical polynomials on inequalities, all we can say is that you can bound this by the exponential of the degree of your polynomial over, say, some a, times by let's say this is p of x, times by the sup norm of p on this interval minus a to a, for any a that you like. So what you're going to see is that when I pass the polynomials from just moments, you're going to get something that depends exponentially in the degree of the polynomial. Right? But exponential dependence is too bad for the polynomial method to work. The worst I can get is something like the worst I can deal with is something that's going to be polynomial in the degree, eventually. But what I'm seeing is something that's going to be exponential in the degree. So what you have to do is you have to go to higher order powers of g to be able to kill this thing off, to kill this exponential growth off, and get it back to something that's only going to be polynomial dependence in the degree. So there's some nuances of why you have to go to larger order expansions of this. But all in all, what you'll see is that when you do a polynomial, for the expansion of polynomials, let's just say up to second order, you can do higher orders, you'll get to these distributions that are coming out, or these functionals that are coming out, but your error term will look something like this now. It'll be converted into something that's polynomially dependent in the degree, times by the sup norm of your polynomial, evaluated on where the whole spectrum gets mapped to under this f hat transformation. Okay, but this is too bad to be able to extend to smooth functions, right? Because if I take a sequence of polynomials converging to my smooth function, this thing will blow up because the degree will go to infinity. So the picture doesn't end here. Okay, and we have formula for the new 0, new 1. It's exactly what I had before, but now I'm just taking linear combinations. Okay, so nothing interesting there. So to get the extension to smooth functions, we need to deal with this error term. And this is a beauty of this polynomial method. What it does is, if I have something that's polynomially dependent on here, I can convert it into sup norm of some derivatives instead. Okay? And that's exactly what we do. So we pass the sup norm into something that will depend on some number of derivatives. The number of derivatives depends on this exponent c here. It's like c to c plus 1. And then you'll just take limits along these polynomials. You'll end up with a new error term, which is exactly what I pointed out before. Okay. And then so all that remains to do is, so we have our expansion, we have our coefficients, we know that they extend to compactly supported distributions because we're going to see errors like this form, which was good enough to extend to compactly supported distributions from something like this. But we want to actually compute their support to be able to see that they disappear on our smooth function. And to do this, we'll just do moments. But because we actually have very explicit formula for this, you can actually do this by hand and compute these moments. And what you'll see is that just by direct computation, we want them support on this minus f hat of 0 to f hat of 0. And this is exactly what you get because there's my nicer formula for these moments. For this thing, remember we ignore the k equals 1 term because that's going to get cancelled with the trivial eigenvalue contribution. Everything else here is something uniformly bounded. But if I have something uniformly bounded here, up to extending this to minus infinity to infinity, this just looks like the Fourier transform of the teeth convolution of this thing, okay, at the point 0. Okay? And this t will turn into a power of this thing. So this is exactly why you're seeing that the moments are like powers of f hat of 0. Okay? And so you can just do very explicit computation to compute the support. It all disappears nicely. You plug it back into this polynomial method, and you get the spectral gap result without ever having to touch long-scale geodesics. It can all be done on a finite scale, so it cuts out all of the horrible, hard geometry that you have to do. And you just look at everything on a fixed scale and never have to touch long-length scales, and it's all passed into these beautiful polynomial inequalities instead, which it feels like magic, but it works. Okay, so I'll leave it there. Thank you very much.